Okay, so in this lecture we are going to talk about some of the other MEMS devices that are used, and you can see them around us. Focus will be on RF MEMS, but we also look at optical devices that use MEMS components and some of the other sensors beyond what we have seen so far. So what is RF MEMS? We are now surrounded by RF systems and the components. Any cell phone that you have nowadays can operate in multiple bands, so each one of the bands is used for transmission and receiving data. You have a certain bandwidth that is assigned to you, let's say at 2 gigahertz with this much bandwidth. And because of the standards and requirements, legal requirements, each system can only operate in a certain portion of that spectrum. So you need to go and, let's say at 2 gigahertz, have a filter that cuts out, let's say, a 10 megahertz portion of that frequency band, and all of the information that you're sending and transmitting can be in that band. However, if you switch transmitter, if you switch to a different station, or you need to use a different band, it's a different frequency, different spectrum. And the signals that we have at RF when we're talking about mobile communications, the receiving end has tiny, tiny signals. We're talking about microvolts and nanovolts. In reality, RF communication, RF transmission of data is very, very inefficient in terms of how much power you're spending to or transmitting around and how much power is received by the people around you. And the reason for that is that your transmitter is an antenna here that is covering, let's say, an area that has, let's say, a diameter of a few kilometers. And all the power that comes out of this antenna is distributed on that area, on such a large area or volume, depending on how you do it. And even if you're transmitting kilowatts of power in some situations, the receiving end is receiving only milliwatts or microwatts of power, and has to convert it into basically extract all the information that is sent out. Now, a typical RF system looks like this. You have multiple antennas for different frequency bands. Each antenna is working optimally at a certain frequency. Once the signal comes through the antenna, it has to go through a filter. You get rid of all the stuff that you don't need as much as you can. Obviously, you cannot be too harsh here because the signal has a tiny amount of power. Then the signal goes through an amplifier on the receiving side and is demodulated and eventually passed on to the display or speaker system. On the transmitter end, you get the data here, let's say from a microphone or the user input, goes through a bunch of signal processing modules, and then comes to a power amplifier and goes to that antenna. The components here that can be passive are this switch here, the filter here, and maybe some of the components that you have here for timing, the oscillators that you can make here for timing. The rest of it, the amplifiers, the mixers, all the signal processing, the digital parts, they are active, right? So what we mean by active is that they take energy from, let's say, a DC source, a battery, and use it to do something on the signal. Passive components can be like relays or switches or filters if it is a passive filter. And VCO here, for example, that you see here, this is a voltage controlled oscillator that is used for the demodulation of the signal or modulation of the signal down here. This VCO is a variable oscillator. It is producing, let's say, a signal whose frequency changes from 1.9 to 2.1 gigahertz. And that variation comes from a change in capacitance, for example. So you may have passive elements that are embedded inside these bits and pieces, these shaded areas. But all in all, it's those passives that in most cases provide the most challenges to you in terms of frequency selection and operation. Now, and they are usually the ones that are the, let's say, more difficult ones to miniaturize. The amplifiers, the electronics, the signal processors, all of that is made with CMOS or maybe some other microelectronic technology. All of that can be very, very compact. The passives usually take more space than your active components. And for that reason, there has been a lot of interest in using MEMS technologies to build these RF components. So we'll go through a few of those in this lecture and then see a couple of other devices as well. So variable capacitors are needed everywhere, especially in voltage-controlled oscillators. We'll talk about oscillators in the interfacing section, and you'll see how a changing capacitor can determine the output frequency. But here's one idea of how to make one. So you have a plate, some springs in terms of those L shapes, and if you apply a DC voltage, by now you know that the electrostatic force will pull down the plate. That DC voltage will therefore change the capacitance between the fixed electrode at the bottom and the moving one at the top. So this could be one way of making a variable capacitor, and this is a picture of the device. Here is another example, same idea but different structure, and here is another example. And in this case, instead of a parallel plate capacitor, which gives you a lot of DC over dy, if you go back to electrostatic transduction section, they use comb drives. And the reason they use comb drives instead of a parallel plate capacitor is that comb drives give you a linear response, right? So the engagement between as you change the engagement between the fingers, the capacitance changes linearly with that engagement. With parallel plate capacitors, it's always 1 over G squared. Now, so these are some examples of MEMS variable capacitors. Why would I want to use a MEMS one compared to an electronic one? Most reasons, well, different reasons could be, could be different reasons for that, but one could be, for example, leakage, one could be linearity, one could be parasitics. All those things can actually affect the performance of a variable capacitor at high frequencies, which I may have a solution for them if I use MEMS. Now, once you go past that, you want to make switches. A switch could be a variable capacitor which has a really small off capacitance and a really large on capacitance. So as you can see here, it could be a bridge that we pull all the way down to the bottom electrode, and then when we let go of our actuation signal, the bridge goes back to the original position. This could be your relay, a mechanical relay. And there are, again, different ways of making it. So this is an initial prototype. Again, we have beam springs, and then the electrode is that plate in the middle of the two sections. Let me get my laser here. So this is your signal line. There's a gap here, and this plate goes up and down and closes the signal line or open it up. Here is a better looking one, right? So, and then the idea is still the same. I have this structure, this bridge that is, and this signal line is cut somewhere underneath this capacitor. I bring it down using electrostatic force or let it go and make a short or open circuit. MEMS switches had a big, it took a long time for their development. This has been going on for at least 15, 20 years. And the challenge was wear and tear. You have these MEMS switches that can last millions of cycles, but in RF applications, millions of cycles is, a 1 megahertz signal. We are not really often switching at those kinds of speeds, but an electronic switch, for example, can go on and off billions and billions of cycles, but the MEMS switch life cycle was like millions of cycles. So there was a huge gap to be covered, but a lot of these MEMS switches nowadays are reliable enough that they can be used in MEMS, let's say, cell phones and other communication systems. Usually still the high-end one. The advantage of a MEMS switch over a, let's say, transistor switch is that the insertion losses can be much smaller. With MEMS, you basically have metal contacts. With semiconductors, transistors, the signal has to go through silicon, which is more resistive, if you want to think about it simply in that way. Then another RF MEMS component in RF systems is timing resonators, timing devices. You need reference oscillators in all your communication systems, to figure out what frequency you want to transmit or receive the signal, to figure out all sorts of things on board, right? So to have your modulator, demodulator, timing signals for your digital circuits and all that. And for making an oscillator, you need a component that is selective to frequency. So basically it lets some frequencies go through and then blocks everything else. A very good filter, in other words. You can make those using electrical components, let's say RLCs. The challenge is that in most cases, the sharpness in frequency domain is not that much. You do not get high quality resonators in electrical domain. So it has been the case that if you wanted to have very good resonators, high Q resonators, you had to use a mechanical one. I guess most of you know about quartz oscillators or quartz resonators. It's a piece of quartz that is vibrating at a certain frequency, and it is used in all timing applications. And we have other similar devices, mostly piezoelectric, for other applications. And this seemed like a good place for a MEMS device. So people have been trying to use micromechanical resonators for timing applications. What you need is a very high Q, so you get a very sharp peak in the frequency domain, basically narrow band, and stable resonant frequency. A resonant frequency that does not change with temperature, for example. And this second part, has proven to be harder than the first part, that you want to have a high Q device. There are tons of ways of doing that, but making that resonant frequency stable has been a challenge. Nonetheless, people have addressed that, and a lot of the timing devices that are used nowadays in your, I think in like SD cards even, are MEMS based. So what can we do? Well, you can use different resonant modes. So here is a flexural resonator. The piece is going, the shuttle is going up and down. These are your springs, and the mass comes from the mass of the shuttle. You get some resonator out of this device, and you put it in a proper oscillator loop to keep it vibrating, basically. You can have these bulk resonators, and they can have different vibration modes. So for example, in this case, a lame mode is where you have a square. In this particular case, two sides are going into, the other two are going out, and vice versa. And with bulk resonators, you basically using the entire structure as your resonator, and for that you get a very stiff compliance, right? So the effective spring constant is large, and therefore the resonant frequencies are large. So these bulk resonators will give you high resonant frequencies. It turns out that if you design them well, you can actually get very high Qs out of them as well. So they're very common. And this is another example of a bulk resonator. I'll show you some other examples soon. This is the device, the one that is shown here. And we actually have solved an example on this as the section in piezoelectric transduction. We actually looked at this as a sample where we have a piece of piezoelectric material sandwiched between two electrodes. And again, in this case, we are hoping to excite the bulk mode. The piece, the rectangular piece is becoming longer and shorter as we force it into vibrations. Why do we want high Q? High Q means that you can pick your operating frequency, your desired frequency better. It is sharper. I have a very, very good filtering of all these other frequencies that I don't want. So that's great for resonators, but we'll see that you can actually couple these resonators to each other and make bandpass filters out of them. And these sharp bandpass filters therefore rely on high Q resonators. Going back to the idea of making an oscillator, one of the parameters that make the output of the oscillator stable is a high Q. So that again is because you're picking that operating frequency very, very well if you have a high Q. What do we mean by high? Well, Qs for MEMS devices, MEMS resonators that are designed to have high Q can range from about 10,000 to more than 1 million. Right? So more than 1 million, I think, just to let you compare that, what that or make sense of it, consider a 1 megahertz quartz crystal or MEMS resonator with a Q of 1 million. What that means is that if you just take this, if you just make it vibrate for with a shock, the ringing will take about 1 second to die off. and this is vibrating at 1 megahertz. It takes 1 million cycles for the ringing to die off. If you think about it in frequency domain, it means that if you look at the spectrum, the output to spectrum of this device at 1 megahertz, you see the resonance peak. The resonance peak is about 1 million times higher than low frequency response. So it's much, much, much stronger. Not only that, but if you look at the sharpness, how fast this drops, the bandwidth, the 3 dB bandwidth is only 1 hertz for a resonator with a quality factor of 1 million and a resonant frequency of 1 megahertz. It's only 1 hertz. So it means that, let's say, if the amplitude at the top is 1, and you look at the 3 dB frequency, which is square root 2 of the peak value, the bandwidth is only 1 hertz, right? This F3 dB is only 1 hertz. And then if you couple these properly to each other, you can get sharper and sharper filters. So this is a bandpass filter made of coupled oscillators, and you can see as you increase the Q, you get lower loss through the filter and sharper frequency response. When we talk about losses, what do we mean? At the MEMS domain, losses can come from different physical domains. Most importantly, usually, is viscous damping. Basically, as your MEMS device is moving, is vibrating, it is in friction with air or the gas around it. That is usually your dominant loss mechanism. You have to overcome the friction with air. If that's a concern, your solution is to operate this under vacuum or lower pressures. The second dominant loss mechanism is support loss or anchor loss. And in this case, what happens is that you have a resonator, you want to have high Q. Q, if you go and look at the original definition, it's about energy lost per cycle. So you want to maintain all the vibration energy, keep it all in that resonator. If you lose any of that energy to the environment, be it through viscous damping or other mechanisms, that lowers your Q. Q support in this case, or anchor loss or support loss in this case, is the energy that you lose to the substrate through where you have connections to the substrate. And let's say for a well-designed resonator, if you put it under vacuum and get rid of viscous damping, you can go from Q of, let's say, tens or hundreds in air to Q of tens of thousands in vacuum. And after that, you're limited by Q support. And going from a Q of 10,000 to a Q of 100,000 will require you to minimize that Q of support. If you want to go beyond that, you have to go and reduce thermoelastic damping, surface damping, all other sources of damping that you have at these scales. But usually, the focus is on minimizing the first two here, the Q from anchor losses and the Q from air damping. So some examples of resonators that you can use for RF applications, for timing applications. Well, this is the simplest, as simple as it can be. You just have a beam that is vibrating in plane. You put one electrode on the left side to force it into vibrations and one electrode on the right side to detect those vibrations. That's it. That's your device, a beam. You want to become a bit fancier, you can use the same beam, but in this case, and again, you have an electrode here, an electrode on top, and this is the beam in between. But in this case, you do not use a bending mode. You use a bulk mode. You make the entire structure stretch and shrink between the two electrodes. You get a bulk acoustic resonator instead of a flexural resonator. And still capacitive, still it's really as simple as a single beam. One of the things about timing resonators is that you want to keep them as simple as you can, because actually a more complex structure with more damping, with more anchor points and things like that will usually lead to having more support loss in the end. So that goes against the idea of having a high Q. So most of the high Q devices that you see are super simple. It's just a beam, it's just a spring that is made of the simplest structure possible, right? Or a plate that looks like a circle or a square. Very, very simple structures. You can use piezoelectric transduction to force this device into vibrations. We've seen this before using the piezoelectric discussion, so I'm not going to spend too much time here. But the magic here is that piezoelectric transduction is much more efficient in terms of converting electrical to mechanical energy or vice versa. And therefore, the signal losses through your resonators will be much smaller compared to electrostatic devices. The challenge is that you have to have a piezoelectric material in your process, which, as we said before, is becoming more common nowadays. Other types of MEMS resonators, as I said, they're usually very simple. When you look at them, they're symmetric. You want to minimize anything that can lead to losses. And a disk could be another object that you can use, and then different vibration modes can be selected. F-bar, film, bulk, acoustic wave resonators are your typical filter devices in your cell phones and other communication systems nowadays. In this case, you put in many cases, a piezoelectric material in between two electrodes, and the vibration mode is basically the one that changes the thickness of that piezoelectric layer. If you do it well, you can have high Q devices made through these structures. And then you can put them inside the same package, couple them to each other, and create filters from them as well. Coupling can be done through mechanical elements, like I have two resonators here, two beams here, and I just connect them together using a beam. It could be through the substrate. Right? So in this case, I have two resonators again, but they see each other. They sense each other through the deflections, the strains and stresses that we have at the bases of these two beams. If they are close to each other, and close in this case, depends on the acoustic wavelength, they will affect each other's vibrations. So what happens is that if you have two similar resonators, all of a sudden when you look at the combined response, you see two peaks, one representing each resonator. Basically you get two vibration modes, as you see on the left side. Go to more complicated structures like this, so you have a bunch of square resonators that are coupled to each other, and if the response of one is like that, the response of the coupled system looks like a bandpass filter. And you see this bandpass filter has a few peaks in here in its passband. These peaks come from different vibration modes of this system of resonators. So coupling, again, as we said, could be through mechanical elements, direct coupling between two resonators. It could also be through phononic structures, and you use different ways, different types of phononic structures to couple these devices to each other, or to block some wavelengths from passing through the structure, acoustic wavelengths, or that's reflecting them back in. So RF MEMS devices, in terms of the number of devices, number of MEMS devices around you, are actually among the highest number of MEMS devices produced nowadays in terms of the value, cost, not cost, the value of the market. I think they're actually at the top of the list now. And the reason for that is that we have everything nowadays that is transmitting data wirelessly. And the RF MEMS components, including mostly filters, but also the switches or variable components, are used increasingly in these applications. Now I want to talk about a different category of devices. These are MOEMS, or micro-optical electromechanical systems. So these are MEMS devices that have an optical port. It could be an optical input port, an optical output port, and sometimes they have input and output. And one example here is a digital micromirror device. So this is a cross-section of this micromirror. I can tilt the mirror to the right or to the left, and because of that I can reflect the light that is incident on it to this direction or that direction. So this is a single pixel in your typical projectors nowadays. You can have a diffraction-based grating type of a MOEMS device, and in this case you have a bunch of parallel beams, and you displace these beams from their rest position, and depending on how far you do this and which ones you move, you can get different constructive or destructive combination of the incident and reflected beams, and that can actually be used for optical signal processing again. So let's just move on to this. So a diffraction-based light valve looks like this, right? So you have beams. They could be actually, in some cases, could be made of dielectric layers. But usually they are reflective, so some sort of a ribbon made of reflective material, let's say aluminum or gold, and by moving these up and down, and the movement now by this time we know is most likely going to be electrostatic, I can get a different optical response out of this device. Why do we like these MEMS devices? Well, why do we want to miniaturize these optical devices? Well, in a typical optical system, what you're doing is that you transmit the signal optically, then you receive it, you have to convert it to an electrical signal, do some processing in electrical domain, and then convert it back to an optical signal and send it off. This is not easy. If you wanted to keep it in optical domain, then you have to, let's say, bring in the optical fiber, put a optical multiplexer in front of it, and go, let's say, from one fiber to 5, or from one fiber to one of the 5 at this end. Again, it's not that easy. Those kinds of systems are fairly complicated. And MEMS provided an opportunity for making micromechanical systems that can process this light, these beams of light. So here's one example where you can actually, by playing with this mirror in between, you can switch the light from one fiber into two other fibers. So the light, let's say, comes from here. If you keep the mirror in between them, the light is reflected into this fiber. If you remove the mirror, it can go into the other fiber. And then you can have arrays of these devices. So you have arrays of these devices that are basically responding to different electrical command signals and routing the optical signal into different channels. In this case, channels are optical fibers. So in the early days of MEMS, the miniaturization that it could have was very exciting to these optical systems engineers. Tons of interesting devices came about. They were not really too hard to make. You needed to make lenses and movements. But the challenge was that, okay, so now you have this Fresnel lens. This is called a diffractive lens or a Fresnel lens. It's made on the surface of the wafer. And it's useless to me if I want to do some signal processing with it. I have to make it stand up like that. So the light can go on the, near the surface of the wafer through it. And I can make mirrors, but the mirrors are flat on the surface. I need to raise them. And then I need to lock them in place. So you have all these hinges and locking mechanisms and all that. Very exciting in the beginning. They made all sorts of interesting optical systems from these. But pretty soon it became apparent that, this is a lot of work. A lot of individual manipulation was needed. And despite the excitement in late 90s, and back then it was just before the dot-com bubble, we had a lot of excitement back then, but things didn't materialize in the way that people assumed, and everything cooled off all the way to, let's say, 5-6 years ago, so mid-2010s, where people started to pick up on this again. And again, because of the widespread, let's say, networks we have for communications, we cannot rely on copper networks as before anymore. This optical fiber that is carrying most of the internet data nowadays. And for that reason, people are going back to optical fiber-based systems. You need these smaller systems and test modules. And there's new developments in this area where people are trying to automate as much as they can from those assembly, come up with new device design ideas, and basically have these MOEMS devices that are now deployable to consumer markets. Digital light processing, we talked about the mirror that could be tilted one way or the other using an electrostatic signal applied to one side of it or the other. We had a movie about this during the live session just this past Tuesday. And what we are doing here is that each one of those mirrors constituted a pixel, but your image is a million pixel image or more nowadays. And therefore, you put that many number of mirrors side by side and control them individually to direct the light towards the screen or off to the side in order to create an image. By a moving image is basically produced by controlling these mirrors at refresh rates that are required for your image. So I'm not going to spend too much time on this because we've seen this before. One interesting issue here is that how do you create color images, right? Because if you're just reflecting the light back and forth, that's great for grayscale or monochromatic pictures or images. But what about color? In order to produce color, so there are two approaches here. One is that you let's say use the red, green, and blue lights and use 3 of these digital micromirrors to produce, let's say, those portions of the spectrum and combine the 3 images and project it on the display. The other thing you can do is that you can have a color wheel that is spinning at a relatively high speed. And what you do is that your DMD now has to work 3 times faster, let's say if you're passing 3 colors, and changes the image on the projected image based on the color. And if you do it fast enough, your eye can be fooled. You will do it fast enough so that the eye will not notice that you've turned off green and now you're only projecting red. And then you do the same thing to blue if you do it fast enough. So in that case, your DMD has to switch 3 times as fast, at least, in order to do the job of the system on the left. But the benefit is that you use only one DMD and your optical setup is relatively simple. Now, here is an example of a device from Lucent Technologies. So these guys were major players in optical communications area. And this DMD, the way it works is that you have this reflective surface. There is a spring here, a pair of them here, and then a pair of them here. They let this mirror to tilt in 2 dimensions. So you can actually have basically go and do whatever you want with the beam of laser that is illuminating this surface. You can point it to any location you want in the plane above it. Now, last topic I want to talk about here is beam-based sensor design. So we talked about cantilevers and we said we love cantilevers when we talk about MEMS. And now I want to show you a couple of examples where we use just a simple cantilever, a simple mechanical element that you have for different purposes. Now, one example is mass sensing. We saw that, for example, resonance sensors, the way they did the sensing was that you had the square root of k over m for the resonant frequency of the structure. If you changed k or if you changed m, you would get a difference in your resonance frequency that could tell you whatever parameter that, let's say, changed mass, how much it was. So you can use that idea, make a resonator from a single cantilever, and then if you add a little bit of mass to it, you can go and figure out how much that mass was depending on the resonance frequency changes. This is the dynamic version where you keep the device under vibration all the time. Another version is that you coat the surface of your beam with something that has a static response. So for example, in this case, you coat it with something that is selective to a particular molecule, some receptors here that are selective to a particular molecule, and if that molecule comes and binds with them, you produce some sort of a surface stress. And that surface stress causes a deflection of the beam. And that deflection is a static deflection. You can measure it and then figure out what was the concentration of the target molecule in the environment. The concepts are very simple, but they have been used in some amazing work so far. One of the most interesting applications of cantilevers in atomic force microscopy. And we've used it as an example before, but here's how the system works. You have a probe that is essentially a cantilever with a very sharp tip. This sharp tip is moved across the surface. If you have topography of something that applies a force to the probe will go up and down in response to the topography of that force. And all you need to do is to have a way of measuring the deflections of this probe in order to say something about what was going on the surface. Most simple case in many situations is to have a beam bounce back from the backside of this cantilever. So you have a laser beam coming and hitting this, and you have a split photodiode here. As this probe goes up and down, the location of this reflected spot changes, and based on that you can tell where it is. These are typical shapes. You can have a straight probe, or you can have this triangular design, V-shaped design for it, depending on what you want to do. You want to choose one or the other. But with these probes, you can just do so much surface analysis. Actually, these were atomic force microscopes, were among those tools that have shown us so much. The STM, let's say, grandfather of all these scanning probe microscopes, brought the Nobel Prize to the inventors. And lots of interesting phenomena have been discovered or analyzed using these AFM systems. Beyond that, I would like to talk about artificial nodes. This is an old example, but in, let's say, late 90s, early 2000s, there was this idea that we can have multiple gas sensors operating parallel with each other, and if each one of them is detecting one gas in the environment, by using the right combination of these sensors and right number of them, we can basically detect all sorts of gases in the environment, or like a nose, be able to pick up different types of smells or stinks in some cases. And those systems existed. We have multi-gas sensor systems, but they're usually large. And to just give you an idea, a good high-quality multi-gas sensor system typically costs upwards of $50,000. So there was room for improvement, both in terms of the size and especially cost. And this is one example from IBM, where they put a bunch of cantilevers here, put a sensitive layer on each one that was targeting a different gas, and using one of those techniques that we mentioned before, through a dynamic measurement or a static measurement, you can go and figure out the gas concentrations in the environment. So they used, let's say, laser beams in order to figure out how much this cantilever bent, and then how much this one bent, and how much this one bent. And that gave them an estimate of the concentration of different gases in the environment. So still an interesting area, right? As far as I know, we still don't have a very good electronic nose in the market. So if you can come up with an idea to make even, some situation, an electronic nose that covers a portion of what is possible out there, a segment, let's say, that you can use in, let's say, bio energy industry, that would still be I would say, good product to have in the market. For mass sensing applications, one could be particle counting, right? So in this case, they're using a single cantilever to figure out how many spores are in the environment. And then the idea here is that, again, by adding mass to this device, you drop the resonant frequency, and therefore you can measure the mass of these tiny, tiny particles. The sensor in this case, as you can see, they're cheating. They're using an AFM probe for doing that kind of a measurement, even though they are not scanning a surface or anything. And then we can, people can be smart, and what they said in this situation was that, okay, let me do biosensing with these cantilevers. The problem here is that if you take one of these MEMS cantilevers and insert it into biosamples, which are usually in liquid form, the damping will be too high. The challenge is that the viscous damping inside the liquid is just so high that you cannot see your resonance. You will lose your resonance signal. So they said, well, why do we want to put it inside the liquid? Let's pass the liquid through the cantilever. So what they did here is that they created a channel inside the cantilever, and you can activate it by attaching certain enzymes to it, and they pass the biosample through it. Now you can still put this cantilever inside vacuum, operate it at high quality factors, and All of the liquid, let's say biosample cantilever interactions are happening inside the cantilever, therefore the Q of the device doesn't damp as much. And if your target marker sticks to your, whatever that you coated the cantilever with, you will have an increase in mass and therefore a change in resonance frequency, which can be measured and figured, basically related to, let's say, the concentration of such and such biomarker in the sample. Test setup, again, because everything is happening inside the cantilever, you can put the actual device itself inside the vacuum chamber, and then the detection was optical. Optical detection, just keep it in mind, is easier than electrical detection or many other detection mechanisms, especially if you're doing a remote measurement, especially if you're doing a measurement on an optical or electrical or electromechanical system, just because that the optical setup can be separated and operate in a different electrical domain. The challenge is that optical setups, well, they are separated, so you need an additional setup. If you can do everything in electrical domain, you can keep your device input, output, all the signal processing in one domain. Optical, it's easier to do the work, but you need to pay for the setup. And these are some of the fabricated devices that we mentioned. Now, what else is there? Well, a ton. There is a lot of other MEMS devices that are routinely used in a lot of applications. You see some of them here. We haven't even touched the microfluidic part other than maybe just this last mention of a fluid going through the cantilever. And that's also a huge field. We may try to cover that if we have extra time at the end of the semester, but there is a ton of other devices, MEMS devices, that we didn't talk about. These are some common devices that everybody is using nowadays. These are up-and-coming devices. So now there is a talk of making tiny speakers using MEMS technology and making actuators for moving the lens of a camera back and forth for focusing, and then all sorts of gas sensors and all sorts of proximity sensors and energy harvesting and all that. The backbone, the prototyping, the proof of concept work has been done, but we are getting into an area or an era that you are actually seeing commercial applications of these devices. So where are we going? Well, 80s and 90s was about just starting the digital era and then figuring out, how to do everything digitally. We lost a lot of good stuff in that time. We lost a lot of analog expertise in that time. But it was easier, so people stuck with it. In 2000s, we started to have communication capabilities added to a lot of our computing devices. Now, they could compute stuff, they can communicate, they could still not sense. They could not figure out what was going on in the environment. And from mid-2000s, MEMS devices added that capability. Now, all these devices, systems that have a computing power and they have communication power, they now can interact with the world around them, figure out what's going on. And the buzzword of the day, or the buzzword of yesterday and so on, is Internet of Things, where you have cars that can talk to each other and to remote servers, and wearables that monitor you, and all sorts of other things, and smart home, and smart city, and smart farm, and all of this is made possible by MEMS. So obviously different types of MEMS for different types of applications, but tons of up-and-coming applications are still out there. So what we want to do so far, we looked at how to design and fabricate MEMS devices, and I showed you some examples of how they actually work inside the package. From this point onward, I want to talk more about how to use them. So the interfacing section of the course is about, if you have a device with a capacitive interface, how do you get the data out of it? Or if it is a resistive interface, how you do that? And once you have the data, then what do you do with that data? How do you make sense of that data? So that's that for the application side. And I'll see you in the next video starting the discussion about interfacing. Thank you.